In the course of the physics of solar energy conversion, we now study the factors determining the photovoltaic. In the previous lecture, we have obtained the expression for the radiative open circuit voltage that is determined by the radiation at one zone, represented by the photocurrent, and the radiative J0, which is the fundamental parameter for recombination, both depending on a single quantity, which is the function of the photovoltaic EQE. So this gives us the maximum possible VOC depending on the properties of light absorption and carrier generation. We want to understand better how the voltage depends on the material parameters. And so we start with the analysis of the photovoltaic. We're going to take the expression of the radiative voltage and we write it into terms. Minus kBT over Q ln of J0 radiative. And we have also determined the expression for the radiative J0, and this is Q and the factor and the integral of the absorption and this integral is from the band gap to infinite. And the integral can be approximated as Q B sub P, the absorption a cap to the square kBT e to the minus G over kBT. So based on this approximation, the ln of J0 radiation is minus the gap energy and another term that contains the other factors . And introducing in the initial equation, we can write an expression of the radiative voltage in terms of explicit quantities. The first thing we see is that the photovoltaic correlates with the energy of the band gap. And this is very natural because recombination is going to set the distance between conduction of valence band as it is going to fix the carrier density, so that this will be the VOC. Now, if we have the same recombination for a larger band gap, then the VOC will be larger. So this is the first dependence. It's a correlation with the voltage. It's also true that for a larger band gap, the current will decrease. The second term is a dependence on photogeneration. So this is also clear that if we have, for example, this Fermi level fixed, the Fermi level for holes, and then we have some irradiation, then we have an initial VOC. But if we send more light in, then the Fermi level of minority carrier is going to rise more, and we will have a larger VOC. Now we can analyze the Shockley-Queisser approach, in which a solar cell or a material is characterized by a sharp absorption at the value of the gap. And then we can see that, of course, the band gap increases linearly, and also does the radiative VOC, which is indicated by this line. Okay. So this is the VOC obtained at one sun illumination, which is less than the band gap by an fixed distance. So far, we have analyzed the photovoltaic in the absence of non-radiative recombination, but this is an important factor, and it's present. We can suppress the effects, improve, but there might be remaining an amount of non-radiative recombination. So how does this affect the photovoltaic? So if we recall that this is the expression for the voltage in terms of the illumination and the J naught parameter. So we have that the actual J naught equals the radiative plus the non-radiative. So that we have to substitute the J naught here, and this will be the actual VOC, and it is less than the radiative, so the VOC is decreasing by the influence of non-radiative recombination. So the actual VOC is smaller than the radiative VOC. This is a positive quantity. This is the voltage deficit in the specific solar cell, and we want to control this quantity. And to this end, we remember the relationship that the EQ LID, this is the radiative with respect to the total recombination current in the dark. So this parameter is useful to quantify the amount of non-radiative recombination. So now we write VOC T over Q this is the sun photocurrent over J0, and this is T over Q with respect to the radiative parameter plus KBT over Q with the fraction of radiative to total. And then this factor is the EQE, so that we can write the VOC in terms of the radiative plus the EQE. So here we see an example of different solar cell technologies indicating the LED quantum efficiency and the correlation to the normalized efficiency with respect to the ideal efficiency of the solar cell. And of course, the LED quantum efficiency is in logarithmic scale, and it correlates with the non-radiative voltage loss very directly, according to the formula that we have obtained. Now we have arrived at a very general and important picture of the photovoltaic in the solar cell. And we have two steps. First, the radiative voltage is depending only on the photovoltaic external quantum efficiency. by determining the flux of solar photons with respect to the iota zero in the limit of radiative recombination. And the actual VOC is less than the radiative by the voltage deficit, and this is decreased by the lead efficiency, EQ LID. The first quantity is spectral and the second is not. So for improving the photovoltaic, then we have to attend these two factors. Obtain a large EQ, it means that we need to harvest the light and convert the photons to carriers, trap the light, etc. The second question is to increase the radiative efficiency so that the voltage is invested in creating photons and not in creating heat. This is mainly obtained by reducing non-radiative recombination. So that these are the main steps in improving the efficiency of the solar cell with respect to the photovoltaic. Here we show specific analysis of two types of perovskite solar cells, and then from the radiative voltage, there are voltage losses. For example, here is 110 millielectron volts for non-radiative bulk recombination and another drop for non-radiative recombination at the interface. Here is indicating in each of the cases where is the main causes of non-radiative recombination. This is the interfacial recombination, and the triple cation perovskite has larger voltage because it has less recombination. In polycrystalline solar cells, grain boundaries are a source of defects that produce recombination. Therefore, the passivation of defects is and removing the interfaces at grain boundaries. This is very important, for example, by heat treatment. In a perovskite solar cell, making a better structure of the grains will improve not only the luminescence, indicating that there is less non-radiative recombination in the grain boundaries. Here is the same. By a chemical treatment, we increase a lot the radiative recombination, as we can see in the picture, where now the grains radiate a lot because the interfaces between grains have been passivated. Finally, we recall the surface photovoltaic, which is a voltage measured by Kelvin probe, and there is no contact at the right. So what is the relation of this voltage to the photovoltaic in terms of the Fermi levels? Well, here, when we shine light to the semiconductor, there is a splitting, internal splitting of Fermi levels, and this splitting of Fermi levels is producing a voltage, an internal voltage difference, and this is precisely the shift of the vacuum level that is measured in surface photovoltaic. So the two things, the internal photovoltaic and the measured surface photovoltaic, are directly correlated.